Got it? All right, I'll begin. Dear Heavenly Father, we thank you for this afternoon. Again, Lord, I thank you for these students. Pray you help us to understand what we have to try to study your creation today, Lord. Try to understand a little bit about special relativity. Just give us clarity of thought and help me not to get lost. In your name I pray, Lord Jesus. Amen. All right. For me, this material is more difficult than what I usually cover in here. So we try to pick up right where we left off. Relativity. Yeah, okay. So we were thinking about two inertially related observers. They start out at the same time and place, and then so you've got your S frame, and then we had our S prime frame, and they were moving. We thought of the S prime frame as being moving with velocity, constant velocity u, as viewed in the S frame, and we derived last time that if we're consistent with Einstein's axioms, it's principle of relativity, and that the laws of physics should be the same in all inertial frames of reference, and also that the speed of light should be constant, then we derived that x prime. So let's see here. This is x and this is x prime, right? We derived that x prime should be equal to, say, gamma times x minus ut, I believe. And t prime was gamma u times t minus, what was it? X over c squared? Okay. Let's see here. Is that right? Doesn't feel quite right. I don't know. Let me just check for a second. This is a great. I had a course once upon a time out of this book. It's Special Relativity Introduction to Special Relativity by Wolfgang Rindler. As a student, I didn't find it especially friendly. This is Introduction to Special Relativity by Robert Resnick. It's a classic. This one's much easier to read, but it's kind of old, but it's nice. Anyway, eventually in here I'll find the right equations that I'm looking for here. Ooh, look, pictures of Einstein. Let's see here. Einstein with a pipe. Einstein with a bicycle. Exciting stuff. Let's see here. Come on. Out with it already. Oh, he's deriving these equations for pages and pages. All right, finally, here it is. So I wonder if I did something wrong algebraically last time. I'll have to review the tapes. But we should have got this, gamma times, excuse me, t minus ux over c squared. Seems like I had an extra u in the algebra last time, so I'm sure there's an error if I remember it right. I knew what I wrote down originally was wrong from dimensional analysis. So you had me at like x over c squared, right? That wouldn't make sense because it would have like an extra unit of length that wouldn't be compensated. And so dimensionally it wasn't good. Now this makes more sense because, all right, so like you've got meters per second times meters, right? Divided by meters per second squared. So you're just left with an extra second. 1 over second in the denominator. So the units of this are correct. So from dimensional analysis, this is more reasonable. Now the gamma is by definition 1 over the square root of 1 minus u squared over c squared, all right? And these are the so-called Lorentz transformations. Now, you can reverse them also, right? So the reverse transformations would be what? X is equal to gamma times x plus ut, x prime, t prime, and y, listen to me, t is equal to gamma times t prime plus ux prime over c squared. All right. Now, there's a variety of different things I want to talk to you guys about today as it pertains to this. Let's start with the problem of time dilation. All right, so what we want to think about is now what's an event? I guess it's an important idea. What's an event? An event is a time and a place. All right? So you've all got invitations to weddings, right? Those are events. They give you a time and a place. And then you just have to think about why to say no. Because we've all got something better to do with our time than go to a wedding. That's for sure. All right. Okay, so what we want to think about is, like, suppose that, and it's my tendency is to put the clock on the S prime and to analyze it that way, but it's just the math is easier if you put a clock here, all right, and you let the clock go through a period of time, all right? So like, well, I like what Shankar says. Shankar says it goes tick and then it goes tock, and those are the two events, tick and tock. It's useful. So as I say, tick is the clock at one point, tock is the clock at the next point, all right? And so this clock is at the origin of S. It's sitting there. It's ticking and tocking and so forth. Then the question is, okay, the question is, for S prime, how long does it take to go from tick to tock? All right? So let's say tick is t equals to 0. Let's say tock is, say, t equals to, say, t naught. I don't know. It's the time between whatever time it takes for the clock to go through a standard increment of however it's time increment. Maybe it's a second. Maybe it's an hour, whatever you want. All right? Tick, then tock. Now, also, what is x equal to? Well, x is equal to 0 both times, right? Now, the notation I like to get in the habit of using, I find it's usually useful, is I like to label events by like capital letters. So for me, I'm going to say this is A and this is B. All right? So I just put a little T sub A, T sub B, X sub A, X sub B. So in the S frame, A has time-space coordinates of 0, 0, and B has time-space coordinates of T naught 0. All right? What about in the S prime, though? Let's see here. So how do we get the events in the prime frame? We have to go back to the Lorentz transformations, all right? So let's see here. We have to do everything. Everything goes through x prime equals gamma times, x minus ut, and t prime is equal to gamma times t minus ux over c squared, okay? All right. So in other words, x a prime, well, here, I'll just do it here. So you add a's, all right? Xa prime would be xa minus ta, x, x. We don't actually care about that. Why am I writing down? Oh, well, ta prime is what? I mean, I have to find the coordinates of the event A in the prime time, sorry. Well, this is gamma times what? Times 0 minus 0, so it's also 0. So s and s prime both agree on tick, because that's how we set it up. We set up s and s prime to be at the same time and place to start with. That was where this whole thing started. That's our setup. How about tb prime, though? Well, that would be gamma times tb minus uxb divided by c squared. Again, xb is 0 because the clock's going nowhere in the s frame, right? Just sitting there, ticking and talking. And so this is 0. And tb is just the time between the tick and the talk. So it's t naught. So we get gamma t naught. And there you have it. The change in time, change in the prime time, is equal to gamma times the change in the time. To be more explicit, change in time prime is equal to change in t divided by the square root of 1 minus u squared over c squared. So in other words, what does the s prime observer say about the clocks in the s frame? I mean, the S frame says a second passed, right? Suppose that this factor is 0.5, So you'd have a second divided by 0.5, you'd have 2 seconds, right? So the the prime frame would say that 2 seconds passed when I say that only 1 second passed, right? That's time dilation. So, in other words, moving clocks do what? Run slow. Now here's the part that'll blow your mind a little bit. You can reverse this calculation, right? And if you put the clock in the S prime frame, right? And you let him hold on to the clock, and then you compare the time on his clock to the time you see, guess what? Same result. You also observe his clock running slow, right? So it's not, it goes both ways. Moving clocks run slow. Like, how can that be, right?
Did they prove that experimentally?
Yes, in fact. So the probably the best known experimental evidence of this is something like this. Here's the Earth, and you've got these cosmic rays, right? Now, we used to call them cosmic rays, but we actually know nowadays that there are these subatomic particles there's something called a muon. All right? Muons are unstable. If you could put one on a table it wouldn't stay there very long. All right, it has a lifetime of like a microsecond. All right, and yet we observe them lasting much longer. Like we can see them. Well, we observe them on Earth, right? So, long story short, it has to be that their lifetime was much longer than a microsecond. And so the cosmic rays getting to Earth is one thing. Let's see a slightly more. Let me, instead of thinking of this as being Earth, think of this as being a particle accelerator. All right. What's a particle accelerator? It's basically this ring. I mean, you guys have seen that Terminator movie. Remember? Thing he turns on the switch and then he kind of melts into the, you know what I'm talking about? We all forgot this movie. No? What is it, T3? I think it's T3. I don't know. They're also forgettable. There's this giant ring, all right, of magnets. And the magnets, what they do is they make a magnetic field go in this like direction. Anyway, long story short, they accelerate charged particles in a big circle, faster and faster and faster, right? You take two protons, you accelerate them near the speed of light, they hit each other, bam, and it creates all kinds of exciting things like muons, right? And then those might travel along, right? The lifetime of those muons, or protons, the protons have a pretty long life, I think, but other exotic particles will last much longer in the accelerator going in the circle at a very, very high speed than they will at a lower speed. In other words, you can actually see time dilation in terms of the lifetime of particles which are unstable. Yeah.
What do muons decay into again?
No, I don't remember what muons decay into. I don't remember. It's a reasonable question, but I don't remember. I don't think I remember.
So something going at the speed of light
Forget.
would be instantaneous travel if you were like going at the speed of light, no matter how far you went.
Start again. I just missed the start of your question.
If I was going at the speed of light,
Yeah.
wherever I went, it would seem instantaneous for me then.
Yes. Well, I guess right. So the famous thought experiment, right, is so you have you twins, right? You have twin A and twin B, right? And then twin A goes out here and then comes back, right? And like fast, okay? Really, really fast. So fast that his time slows down. Suppose he goes such that gamma is equal to, say, a factor of 10, right? That would be near the speed of light. I don't know what do you need to get 10, you'd need this to be like 1 over 100, right? So like, I don't know, whatever that's got to be. It's close to C anyway. You can make gamma as big as you want, is my point, by getting arbitrarily close to C, okay? So if that was the case, if this guy stayed put, right? And suppose he aged 10 years, all right? Then twin A, the one that went on the trip and was always going at so fast that he was going at gamma equal to 10, then he would only age 1 year, right? And yet his twin would be 10 years older.
Is there something where like he turns around so that changes something? I saw some video on.
Right, people say, well, that's a paradox, right? Because you could just as well think about, from twin B's perspective, A is going, he's going really, from twin A's perspective, twin B is going really fast, right? So he should should age slower or whatever, right? But the thing is that it's not symmetrical, right? One of these is accelerated and one of these is not. There is a clear difference between A and B. B does not accelerate, whereas A does. And therein lies the resolution to the paradox. Now, I can't explain it worth anything. I admit that. If you want to see this clearly explained, all you got to do is watch Shankar's second video, minute 40 to the 60-minute. Right in there, he explains the twin paradox and length contractions, like how it can be true for both frames but not agree, the departure from simultaneity, all this stuff he explains far clearer than I can hope to. All right, so if you want to understand those things more deeply, go watch that. That is my best advice to you. I would love to tell you that I have gotten to the point I can clearly communicate it. I do not think I'm there. But that's with the twin paradox, that's the thing, is that they're not the same, so they don't have to observe the same thing. One's accelerating, one's not. So the next thing is length contraction. Length contraction. So there, the question is, if we measure some rigid object, right? So suppose you have some ruler, right? Length L, say L naught, in S, and then, of course, you're thinking about S prime again. You want to compare length L naught in S versus the length in S prime. It all is about events, all right? You have to identify events, and you feed the events to the Lorentz transformations, you transform them, that's how we derive things, all right? So how do you actually measure the length of a ruler? What do you need? You need two events, right? So like, what do we do? Let's say event A and event B. What are my events? A would, let's say, XA equals to 0, and what's TA equal to? I mean, whatever you want. When do you want to measure the length of the ruler? I suggest we measure the length of the ruler at time 0 for our convenience, right? Seem fair? I mean, you can measure the length of the ruler at some later time if you want, but let's not do that. The B coordinate of the ruler would be L naught, right? And when should you measure what? I mean, when you measure length, you don't do it. I mean, ideally, you should do it at the same time, right? At a fixed time. So TB is also what? Oh, I think I'm getting confused here. Oh, man. Oh, I'm not confused yet. Let me just not despair. Let's go on. You have to understand, I have certain psychological problems here. Wait a minute, no. Spiritual problems. It's better. Oh, it's better because one is real. All right, sorry. Anyway, so what would the corresponding events be? I don't know if I've set this up in the right way. Well, let me just stick with it and see if I can interpret it properly. So what's XA prime? Gamma times what? XA minus what? Minus U TA, right? And what's XB prime? I think the mistake I've made here is before this point, Shankar has derived the velocity transformation stuff, and then he uses delta x and delta t relations. It makes it much simpler. I think this is the trap I've fallen into. I was like, well, I'm going to do this first, and then I'm going to show you guys how velocities transform. That was probably a mistake on my part, pedagogically. But anyway, we're okay, I think, logically speaking here. These are 0, right? And so what we have is xa prime is equal to what? 0, because xa is 0, right? And what's xb prime? Gamma times L naught, right? So what do we have? We have that the change in x prime, right, is equal to what? It's equal to, I guess you could say L prime gamma times L naught. So I'm saying change in x prime. Ah, I've messed it up. Ah! Curses. Let me fix it. Just a second. Mulligan. All right. It's a how to say this. My problem is one of interpretation, guys. I think length contraction. So the I mean, I don't think anything is wrong with the equations I've written here. The problem I'm having is one of interpretation, okay? The slogan is length contraction. In other words, the longest the ruler will be is what? When you're not moving, right? So the ruler in the rest frame has the largest length. And I suppose that's what this says, right? The ruler is at rest in the S frame, right? And the length measured in, that's the thing I'm not sure if it's fair to say that I've measured the length. I don't think I've really measured the length in the S prime frame. If I'm measuring the length of the ruler in the S prime frame, I should do it for equal prime time. I've measured the length in terms of equal S time. That doesn't tell me what the length is in the prime frame, right? To measure the length in the prime frame, I should do it at the same prime time. All right. Bear with me here. Here we go. Imagine a rod lying at rest along the x prime axis of the S prime frame. Its endpoints are to be measured at x2 prime and x1 prime, and its rest length is x2 minus x1 prime. All right, so here's the rod. It goes from x1 prime to x2 prime. All right. It's lying at rest on x prime axis, all right? What is the rod's length as measured by the S frame? Observer for whom the rod moves with relative speed u. There we go. All right. So the Lorentz equations are then what? We have x2 prime equals what? Gamma times x2 minus what? ut2. And x1 prime equals gamma times x1 minus ut1. All right. So x2 minus, what's x2 prime minus x1 prime? I'm sorry? Yeah, change in x prime, fair enough. But what is that? In terms of these equations up here, it's gamma times what? It's gamma times what? x2 minus x1 minus u times t2 minus t1, right? They have the same gamma factor if you take the difference. In other words, you could also write this, and we'll use this for the velocity transformation shortly. This says that like change in x prime is equal to gamma times change in x minus u change in t. That actually we'll need in a couple minutes for the velocity transformations anyway. I feel better about my life. All right, so then what? Now here's the thing. The length of the rod in the S-frame is simply the distance between its endpoints x2 and x1. All right? And so distance, length of rod in S-frame is x2 minus x1, okay? And if you're measuring the rod in the S-frame, what do? You measure both endpoints at what? The same time in the S-frame, right? So T1 is equal to T2 in this measurement of length, right? So if you do that, what do we obtain? We obtain x2 prime minus x1 prime is equal to gamma times x2 minus x1. In other words, the length in S is equal to the square root of 1 minus u squared over c squared times, the length in the prime frame, the rest length. And that's length contraction, because the square root of 1 minus u squared over c squared is always something smaller than 1. Its reciprocal is always something larger than 1, right? So gamma is the reciprocal of the square root factor there. And that, folks, is length contraction. Sorry, I found a way to be confused about this. But like the comparing of events I was doing to start with wasn't useful. I need to think about the rod moving and measure the ends of the moving rod at the same time, right? In order to calculate its length in the moving frame. That's the thing. Sorry. I tried to not do this to you guys. I was successful over here in the time dilation. There's also this danger of doing it wrong for me pedagogically. But anyway. All right, so there you go. This is length contraction. And if you watch Shankar's second video on relativity, like especially minutes 40 to 60 or so, he uses the combination of time dilation and length contraction to explain away a number of paradoxes. And you start to see how these two things work in concert, so that even though the distance between events and the time between events is not the same for different observers, they can both come up with understandings of why it was different for the other observer in terms of why they're moving and things. For example, he looks at light clocks to understand this relation, how you could have this difference in measured time. But I'm gonna go on here. Velocity transformations. I mean, okay, getting back to your homework, it's pretty simple, right? You either divide or multiply by the scale factor, right? So if you could just remember these simple slogans, moving clocks run slow and length is contracted, so its longest length is its rest length. If you remember those two things, you can do all the problems that are based on time dilation and length contraction. It's much harder to derive, in my opinion, than it is to use. Okay, so that was, we have change in x prime is like this, right? So I need to talk about velocities for a second here. Velocity transformations. So I already just derived for you change in x is equal to gamma time, change in x prime is equal to gamma times change in x minus u change in t, right? And you can likewise derive that the change in t prime is what? Let's see here. Almost the same calculation is going to give you change in t prime is gamma times change in t, right? Minus what? U change in x divided by c squared. All right, now that's just comparing two events with respect to two different initial observers, right? We're comparing an event 1 and an event 2 for frame S, and event 1 and event 2 for frame S prime. Now let's suppose that those two events are connected. Let's suppose that these two events describe what? Like, so here's, event 1, over here event 2, let's say. And, let's suppose that those actually are correspond to the motion of some physical object, right? Then what would change in x, and suppose one dimension, just to keep it simple here for a minute, what would change in x over change in t be? That would be its average velocity, right? That would be the average velocity of the particle in frame S, right? What would change in x prime over change in t prime be? That would be its average velocity in S prime. And you might wonder, how do these compare, right? Now we know that the Galilean rule, as we discussed last time, is what? It's just simple addition, right? If you're in a train going 50 miles per hour, and you throw a baseball 20 miles per hour in the direction of the train, the person who's not in the train and who observes this sees you throw a ball 70 miles per hour in the forward direction, right? Relative velocity, just add. Or subtract if it's against the motion, right? So, to discover the velocity transformation rule here, what we can do is just divide delta x prime by delta t prime, and then think about taking the limit as delta t prime goes to 0. That should give me the instantaneous velocity. So here we go. Delta x prime over delta t prime, right, is equal to what? Oh, first of all, the gammas cancel. That's pretty sweet. See that? There's a gamma upstairs and a gamma downstairs. They're gone. And then what do? If I want to convert it to, like, let's say that the instantaneous velocity, we could say that this goes to v and this goes to v prime, okay? Let's see here. So if I divide the top and the bottom by delta t, that should give me something, right? So like delta x over delta t minus u divided by 1 minus u divided by c squared delta x over delta t. Then let delta t prime go to 0 and obtain v prime, right, is equal to what? V minus u over 1 minus uv over c squared. Excuse me. Now, what would happen if what if I wanted to find the reverse transformation, right? Instead of no. What if I wanted to find v in terms of v prime? How would that be? How would that go? I mean, you could think about these equations, right? You could calculate the change in x versus the change in t versus x prime and t prime and so forth. You could go through the same calculation, and you just would have, what would be the difference? You wouldn't have minuses here, you'd have pluses, right? And you'd get what? V is equal to v prime plus u divided by 1 plus u v prime over c squared. So there's the other. So that to me is, for some reason, more useful to think about. So if I was on the train, right, and I threw the baseball forward, then the velocity you'd observe would actually be smaller than the Galilean, what the Galilean relativity tells you, because it wouldn't be 20 miles per hour, plus the velocity of the train. It would be 20 miles per hour plus the velocity of the train is u, velocity of the ball is v prime. Then you divide by this number, which is larger than 1. So it's smaller, right? And what happens here? If you take the limit as Shankar points out, if you take the limit as c goes to infinity, you get back to what you'd think of in terms of like Galilean relativity, right? If c goes to infinity, this thing is gone, and you're just left with v is equal to v prime plus u, and vice versa over here. You just get v prime as v minus u. So it's rather satisfying. I mean, you could think of ordinary physics as some kind of infinite. If you let the speed of light go to infinity, that kind of returns you to the Newtonian world. Yeah.
So even though you are adding a change in the velocity plus whatever your train velocity is, and you're dividing by some number that's larger than 1, but is it barely at all larger than 1?
What's that?
Is it barely larger than 1? Like
Well, yeah, I mean, exactly. For the actual thing I was talking about, unless your train actually is going near the speed of light,
yeah.
and I could throw a lot harder than I can, no, it's not that interesting. Fair enough. These are hypothetical comments I'm making, of course, yes.
So would Galileans in practical sense work?
Could what?
Would Galileans, like, would his observations work in the practical sense? Just adding velocities?
Yeah, I mean, yes, the physics we've covered up to this point is very, very good for everyday ordinary existence, yeah. You really need to go to something like a particle accelerator to really, field trip to appreciate mechanical examples of special relativity. I think that there are implications of special relativity in terms of, like I was talking about, radioactive particles lasting longer than they should have and things that you might be able to. There are applications of special relativity to everyday life, I think, but none of them are going to be so direct as me throwing a ball on a train that, all right. Now, I want to show you some math, if you don't mind. So this is awkward so far. Everything I'm doing here is just horribly awkward. There's a much better way to write these equations. X prime is equal to, well, gamma, fine, that's good. But we should really write this x. Okay, fine. I'm just gonna let me just write them down again here, and then I'll convert them to the prettier things. Minus ut, fine. That was what we had. T prime is, what was it, gamma. times t minus what? Ux over c squared. So what you can do is introduce more sort of equal what's the word here? Symmetrical coordinates, let's say. You can let x naught, all right, equal to ct, and you can let x1 equals to x. And we'll also introduce beta. Beta is going to be u over c. So 1 over the square root of 1 minus u squared over c squared is just 1 over the square root of 1 minus beta squared, which is an improvement. There's less writing of c. So if you introduce this ct as the basically rescale time by the speed of light, it makes the formulas much nicer. So in terms of this language, we then have x naught prime is equal to gamma times x naught, or whether x1 prime is equal to x1 minus. All right, so the thing is, I can take ut, multiply by c, and divide by c, and that gets me minus beta x naught. And then x2 prime is equal to what? Well, x2 prime, listen to me, x naught prime, the time one, the 0th one, x naught prime is gamma times x naught. So what I have to do is multiply this by c. It's like multiply by c. Multiply by c, that would give me x naught prime, right? That gives me x naught. Over here, see, I get rid of one of the c's to change the x to x1, but I've still got left over a u over c, which is just beta. Now, in this case that we're just moving with constant velocity in the x direction, there are two other Lorentz transformations, because really, I mean, motion is not one-dimensional, right? So what's the rest of the story? What about y and z? Those equations are those are easier to write. So if you also say, x2 is equal to y and x3 is equal to z, the remaining transformations are like x2 prime equals to x2 and x3 prime is equal to x3. It's rather, yeah, there it is. So what do you think? Are the velocities, like if you look at the velocities in the y and the z direction in the s frame versus the moving frame, are they the same? Are they different? How are the transverse velocities related? You could ask that question. I'm going to just one more step here, and then I'll address that question. If I can find a marker that's working better. Second. That green marker never shows up very good on the video. All I got is red. I guess I'll deal. So you can rewrite this as follows. x0 prime, x1 prime, x2 prime, x3 prime is equal to this 4x4 matrix. In fact, it's this one's first. So it's actually gamma minus gamma beta minus gamma beta, gamma, and then all zeros. This kind of matrix is usually denoted something like this. This is a Lorentz matrix. I guess let me finish. I'll get back to that eventually, but I forgot. What about the velocity? What about the y and z velocities? Like, what if how would delta y, delta t prime versus delta y, delta t. How would those relate? How are those connected? They're the same thing? I would almost agree with you, except there's a thing. The y's are the same, right? But the t prime and delta t are not the same, and that's the rub. T prime is what? It's delta t minus u delta x over c squared, yeah? And so if we divide this by delta t, we get delta y delta t divided by 1 minus, oh, I forgot my gamma. There's a gamma, right? And this time it doesn't cancel because there's no, see, the reason the gamma canceled in the previous one, there was a gamma here and there was a gamma there, right? See? From these? Oh, I'm sorry. Where did I write those? Up here. See, these two give me gamma and gamma. But you got gamma over gamma, and they cancel. It's gone. On the other hand, over here, my delta t prime's got a gamma in it, but there's no gamma in the delta y prime when I change it to delta y, right? So there's no, like, the gammas, we're stuck with it. And so the formula, I divide by delta t, I got 1 minus 1 u over c squared, delta x over delta t. Now delta x over delta t is a thing. What's 1 over gamma? Well, 1 over gamma is the square root of 1 minus u squared over c squared, right? And so what you got here is the velocity in the y direction times the square root of 1 minus u squared over c squared divided by what? 1 minus u times the velocity in the x direction of the particle we're talking about divided by c squared. So that's what the velocity in the transverse direction looks like. So there's an asymmetry in the velocity transformation rules. And that's not too surprising, right? The velocity transformation is really different in the direction of the motion when the two frames are moving relative to each other in the x direction. Then the rule for that transformation is different than the rule for the transverse transformations like the y and the z. But anyway, they still disagree on what time is, so that's why there's some relation. The rule for z will be just the same, right? The calculation is no different for z. I won't do that one. Okay. Oh, something else I should tell you guys. So, any questions about that? No? Yes. So, it's sometimes convenient to, let's see here how to say this. You can rewrite the Lorentz transformation in terms of what's called the rapidity. What's the rapidity? Rapidity is defined as follows. It is the if the hyperbolic tangent of, I think it's, how's it go? Hyperbolic tangent of the rapidity. We usually use phi for the rapidity. That would be equal to u over c. What's the hyperbolic tangent equal to, though? It's sinh phi over cos phi, right? cosh phi is positive, right? So you know that cosh squared phi minus sinh squared phi is 1. So that means that cosh squared phi is 1 plus sinh squared phi. Not sure that helps me. Well, I don't want to... Well, I mean, it's true, but I'm trying to derive for you guys at the moment algebra. ... Eventually, we can derive that gamma is equal to hyperbolic cosine of phi, and no. I tell you, this fan at certain times really gets on my nerves. This is not hard. I believe the gamma... it ends up being this. Gamma is cosh phi, and gamma beta is sinh phi. That's what happens. I'm not seeing how to derive it clearly at the moment because I'm an idiot. I mean, you can see that if this is beta, right? So you can see that this is consistent, right? I mean, if gamma beta is sinh and gamma is cosh, then of course this divided by that gives me beta, right? But admittedly, there's a jump for me right here. But anyway, that's just how the cookie crumbles today here. So I'll have to leave that jump for you. My point, though, is that this just looks like cosh phi minus sinh phi minus sinh phi cosh phi, and then ones. You know, same thing. Do you guys know what a rotation matrix looks like? If you rotate, what if you like rotate by angle theta? How do you do that? I wonder if you guys knew that to do that, you multiply by some angle, some matrix like this. So what I'm telling you is that hyperbolic sine and cosine are analogous, all right, to cosh and sinh in this way. So in some sense, this Lorentz transformation is some kind of like hyperbolic rotation, right? Physicists call this kind of thing an X boost. So anyway, there's that. All right. You say, well, why would you care about rapidity? I mean, are you just inventing more symbols and things to confuse me? That may have been my purpose, I'll admit it. But no, actually there's a good reason to talk about rapidity. If you look at this, right? The velocity, maybe this one. If you look at this, the velocity, if you shoot a gun on a moving train, the velocity of the bullet as measured by the rest frame, it's kind of in a complicated way related to the velocity of the bullet and the velocity of the train. But here's a result that's interesting. If your train has rapidity theta 1, and you shoot the bullet in the direction of the train with rapidity phi 2, so suppose the train has rapidity phi 1, the bullet has rapidity phi 2, then relative to you guys, the rest frame, the bullet will be moving with rapidity phi 1 plus phi 2. So you recover linearity, like the linearity of addition, like velocities do